Hi everyone, this is Mr. Cervone. Welcome to my math channel. In today's lesson, we will learn the following three theorems pertaining to medians of a triangle in coordinate geometry. The first theorem says that the medians of a triangle divide the triangle into 6 triangles of equal area. The second theorem states that the centroid of a triangle cuts each median into a 2-to-1 ratio. And the third theorem states that the coordinates of the centroid of a triangle are the arithmetic mean of the x and y coordinates of the vertices. So first, we'll prove these theorems, and then we'll look at some examples. So let's get started with the first theorem. The medians of a triangle divide the triangle into 6 triangles of equal area. Now here's the word medians. What is a median of a triangle? So as we learned in previous lessons in geometry, a median is a segment that connects a vertex of a triangle to the opposite midpoint of the segment of a triangle, okay? So basically imagine that you have a midpoint here, okay? And what you want to do here is now connect the vertex to the midpoint. Let's label the triangle first. Let's say this vertex is A, this vertex is B, and this vertex is C. So that means that the first median that connects, let's say, C to point D is considered a median. So there you go, is the median CD now. Okay, so we can do the same thing for, let's say, you take the midpoint from segment AC, and then you connect the vertex B to that midpoint. Let's call it F. So then we end up with another median. And then we can draw another median from A to E as shown in the figure. Notice that all these medians are concurrent, which means that they all meet at this particular point. Let's call it point G, okay? So here we're saying that if you draw all the medians, then all these areas here, if you take this area over here, this area, this area, this area, and this area, and this area, so we have 6 areas in total, we're saying that all these areas are equal. How would you prove that? Well, it turns out that this is a simple proof, okay? For example, let's consider area, let's call it BEG, okay? Usually areas are denoted in square brackets, so we're talking about this area over here, okay? Here we're saying that, for example, that is equal to area EGC, okay? Now, why can we say that these two have the same area? It turns out that you know that the area of a triangle is equal to 1/2 times the base times the height, okay? So for example, if you, let's say, focus on this one, what is the area in this case expressed as base times height? Well, in this case, let's write it down. The area of BEG is equal to 1/2 times. Now, which one is the base here? We know that the base is segment BE. Okay, so let's write that in, BE. Times, and then we have the height. So the height, keep in mind, has to be perpendicular to the base. Now, let me use a different color so you guys can see it better. Now, if you draw the height in here like this, okay? And let's call it, I don't know, the first height H1, okay? So we multiply that by H1, okay? Now, you can do the same thing for the other side. Here we can do the same thing, right? For this part. So here we can say that the area of triangle EGC is equal to also 1/2 times, but now the base here goes from C to E, times, and again, here we have H1 to be the height, okay? Because they share the same height. And that is really the key, that those two triangles, BGE and triangle EGC, they share the same height, H1 over here, okay? So another thing to notice is that these two segments here, so let me highlight it, segment BE and segment CE, they're actually equal in measure. So if you look at this, we can actually denote it on the diagram that this and this have to be congruent, right? They're equal in measure. Why they're equal in measure? Because E is the midpoint of segment BC, because segment AE is the median. And by definition, the median goes to the midpoint of the segment opposite of the triangle. So look at this. If BE is equal to CE and H1 is equal to H1, and we know that 1/2 is the same as itself, then we can say that these two areas are the same, okay? So now we just proven the first part, that these two areas of the two triangles are equal. Now what about the other ones? Now, since the areas of triangle BEG and triangle EGC are the same, let me rewrite it as areas X and X here, okay? So I'm going to say that this area is X and this area is X. So they're equal, okay? Now we can actually repeat the same process for, let's say, the, triangle. Let's call it triangle AGF and triangle or area of triangle FGC, okay? Now, again, these two areas have to be the same, okay? Because if you now draw the altitude here, so again, I'm going to use a different color. If you draw an altitude like this that is perpendicular, again, you have 1/2 times base times height. Also with the understanding that, that this is the midpoint, and therefore F is the midpoint and these two sides are congruent. So what happens is that these two areas are also the same, okay? So let me denote these two areas as Y and Y. So you basically do the same process as we did before. Now, what do you suggest about these two? Again, they share the same height here, H, okay? And these two bases, segment BD and DB, are also congruent. And because of 1/2 times base times height, they share the same height, they have equal bases. Therefore, we can also say that area of triangle AGD has to be equal to area of triangle BGD, okay? And let's call this Z and Z. Okay, we're actually almost done here. The only thing we need to prove now that all these 6 areas are equal. And how do we do that? Well, let's now focus on triangle ACD and BCD. So what can you say about those two triangles? Do they also have the same area? And it turns out that yes, they have the same area. Again, if you, let's draw an altitude here. Let's say you draw the altitude from C like that. Okay. So that means that if you call this H, and now let me use the same color. So you have triangle ACD, okay? That has to be equal to 1/2 times the base, which is segment AD times H, okay? And similarly, we have triangle, let's call it BCD. That is 1/2 times the base of BD times the height H. Again, why they equal? Because we know that since AD is equal to BD, and again, why they equal? Because point D is the midpoint of segment AB, right? And we know that H is equal to itself. Then we know, therefore, we know that triangle ACD is equal to triangle BCD. So that actually simplifies a lot of things, because if we know that these two are equal, then we can actually say that 2y plus z, so let's write this in, 2y plus z has to be equal to the other triangle, which consists of 2x plus z. 2x plus z. Okay, so now we can actually subtract z on both sides. So we're actually left with 2y equal to 2x. Therefore, we can say that x has to be equal to y. So there's already the first part of it. We already proved that x is equal to y. Therefore, all these 4 triangles are equal. Now, the only thing left to do is prove that z is also equal to x and z is also equal to y. And how do we do that? Well, now we can look at the other triangles, okay? For example, we can look at triangle CAE and triangle BAE. Again, they share the same altitude, and I'm going to use now a different color again. There you go. So now this is the altitude. So that's H. And again, here we have triangle CAE. Let's write this in. Triangle CAE, which is equals to 1/2 times. So the base here is CE times the height. And for the other triangle, BAE, we have 1/2 times the base, and in this case the base is BE, and times H. Again, they share the same height, and we can also say that CE has to be equal to BE. So why can we say that these two are equal? Again, because E is the midpoint of segment BC. So since we know that, now we can come up with the other equation in terms of x and y. So let me change color. So here we know that now, let me erase that. We know that 2y plus x is equal to 2z plus x. So let's write this in. 2y plus x is equal to 2z plus x. Again, we subtract x on both sides. We end up with 2y is equal to 2z. Therefore, here we know that y is equal to z, okay? Now, look at this. Look at these two equations. If x equal to y and y is equal to z, therefore, by the transitive property, we can conclude that x is equal to y is equal to z, okay? And that is basically the proof. We just proved that all the areas are equal, that all of them are equal. X, y, and z, they're all equal, okay? So we just proved the first theorem. Now let's go to the second theorem. So the second theorem states that the center of a triangle cuts each median into a 2-to-1 ratio. So how do you prove this one now? This one can be proven using what we just learned previously with the areas of a triangle, right? Basically, it's the previous theorem that we just learned, that the medians of a triangle divide the triangle into 6 triangles of equal area, okay? So if you, for example, look at area of triangle, let's say AGB, how does this compare to the area of triangle BGE? Okay, so here we have this area, and we're comparing it with this entire area over here. Maybe I actually should use a different color so you guys can see it better. There you go. How does it compare with this area? Well, as you can see, since all of them have the same area, let's call it area X, X, and X, we know that the area of triangle AGB is equal to 2 times the area of triangle BGE, okay? It's kind of like saying that this is 2x and just this is x. So you have to multiply the x by 2 to get it equal to, okay? So how does this help? Well, what we can do here is, again, look at the altitude and look at the bases, okay? So for example, if you look at the area of triangle AGB, we know that that is equal to 1/2 times the base. Now we have to think about, okay, which base are we taking here? And let's take base AG times the altitude H, okay? Look, and I know it seems a little bit confusing, but let me highlight this a little bit. So we have a base here. That's the base AG, okay, if you can see it. And now the altitude, it seems a little strange, but the altitude is located here. So let's say you extend this line like this, okay? And the altitude is perpendicular to the base of AG and perpendicular to it, okay? In a similar manner, we can now find the area of triangle BGE, which is equal to 1/2 times the base. Now in this case is GE, or let me call it EG, times the same altitude H. And that's a great thing because now they share the same altitude H. And we want to see what the ratio is between, for example, AG and GE, okay, or EG. So what we can do here is divide these two. Let me actually draw a better line. So we're going to divide it. And once you divide it, you're going to see a pattern here. So let's do that. So here we have AGB over BGE. So those are the areas, is equal to 1/2 times AG times H over 1/2 times AG times H, okay? First of all, we cancel 1/2. We divide by H because, again, H is not 0 in this case. And we're left with AG over EG should be down here, okay? EG. Now, we can now substitute because we know that AGB is the same as 2 times BGE. So we're going to write 2 times the area of BGE over the area of BGE, and that is equal to the length of segment AG over the length of segment EG. Again, these areas cancel. We're actually left with a 2-to-1 ratio. And if you think about, we just proved it, right? The centroid of a triangle cuts each median into a 2-to-1 ratio, okay? So you're comparing now the following two, okay? So let me use a different color here. So you're comparing segment AG and segment EG, and it turns out that this is a 2-to-1 ratio, okay? That's what has to be true here. And this is actually true for all of them. So let me draw a separate triangle so you guys can see it better. So let's say you have a triangle ABC. The medians are drawn and they intercept at one point here. So that means that the medians, or that the centroid, in this case, the centroid G, divides each median into a 2-to-1 ratio. Okay, so this is 2 and this is 1. In this case, this is 2 and this is 1, and this is a ratio of 2-to-1. Okay, so that's how they're being divided. Okay, so let's prove our last theorem for today. The coordinates of the centroid of a triangle are the arithmetic mean of the x and y coordinate of the vertices. Okay, so in this theorem, we're saying the following. Let's call vertex A to have coordinate x1 and y1. Let's call it B here. Has a coordinate of x2 comma y2, and coordinate at point C is x3 comma y3. So we're actually saying that the centroid G will have coordinates of x1 plus x2 plus x3, everything over 3, comma, and then we have y1 over y2 plus y3, and everything over 3. So we're saying that, and that's what we're trying to prove here, okay? So how do we do that? So let's get started designating the coordinate at point E, okay? So we know that E is exactly in the middle between between point B and C. So that means that that is the midpoint. So we can write here that this is x2 plus x3 divided by 2, comma, and then here we have y2 plus y3 divided by 2, okay? The next thing we can do here is to look at this segment. So let me use a color here. So we're going to look at this segment here. And now we have point A, right? We have point E over here. And what we want to do is use those 2 points with the information that this is a 2-to-1 ratio over here, okay? So let me draw this separately so you guys can see it better. And maybe we can use what we learned in previous videos about dividing segments into ratios to figure out what is the coordinate at G. Okay, so here's a segment AE drawn separately from the diagram to make a little bit more sense of it. So here we have point A and point E. Let me designate point G as xg comma yg, okay? And our goal is to figure out, okay, what is xg and yg? Now what we can do here is draw similar right triangles. And we can actually then use proportions to figure out the coordinate of xg and yg. So let's draw it in first. Okay, so we draw the right triangles. We know they're similar because they share the same right angle, or they're congruent, and then they share the same angle over here, okay, at angle A. Now we know that those two triangles are similar. Now this point over here is going to have an x coordinate of xg, comma, and the y coordinate is going to be y1, okay? Similarly, this point over here is going to share the same y value, or let's say first the x value, so x2 plus x3 over 2, comma, and we have the same y value as y1, okay? Now, we can use right triangles here, again, the proportions. But before we do that, let's first say that, that this has a ratio of 2, and the ratio of this whole thing is 3, okay? So what we can do here, set up a proportion now, and say that, okay, 3 over 2, so we're comparing the big triangle to the small triangle, is equal to, so the big triangle has this distance here, okay? So this entire distance, that's the big triangle. So the distance is going to be x2 plus x3 over 2, and then we subtract x1, okay? And then we're going to write everything over. And what about the small triangle? Again, I'm going to use a different color. So over the small triangle, which is this distance, okay? So that distance is just going to be xg minus x1, okay? So now all we need to do is solve for xg, and that's it. And then we have the x coordinate. So how do we do that? Well, let's multiply the denominator on both sides. So we have 3/2 is, or times xg minus x1 is equal to, and what we can do here is find the common denominator. So we have x2 plus x3 minus 2x1 over 2, okay? And that's actually great because the 2's cancel by multiplying 2 on both sides. And now we have 3 times xg minus 3 times x1 is equal to x2 plus x3 minus 2x1. Now, if we add 3x1 on both sides, we end up with the following. That 3 times xg is equal to x2 plus x3, and now we have plus x1, which is great. So that means that xg is equal to, by dividing 3 on both sides, x1 plus x2 plus x3, and everything over 3. And there you go, we have the first coordinate. It's the average of all the x coordinates of the vertices, okay? We can do the similar thing for the y coordinate. So for the y coordinate, we're going to draw a segment from G that is now parallel to the horizontal, okay? Okay, there you go. And now we again have two similar right triangles, okay? We can prove it easily because these two angles are right angles, they're congruent, they share the same angle here, so a similarity postulate, we can come up with a proportion. Now let's establish the coordinates here and here, okay? So we know E has the coordinates that were previously given, okay? So now we just need to find the other coordinates. For example, what is this coordinate over here? So here we have the same y value, okay, and the same x value as E. So here we're going to write that this is x2 plus x3 over 2, comma, but now we have the same value as yg, okay? And what about this one? This is also going to be x2 plus x3 over 2, and this y value is y1, okay? Okay, since we're now comparing the ratio of the small triangle to the big triangle, now we know that this here is 3, And we are comparing now this small segment, okay? And that small segment now has a ratio of 1, okay? So it's 1 to 3 now in this case, small to big triangle, okay? Okay, so now we want to write this down. So let's do, for example, the ratio of the big triangle to the small triangle. So it's 3 to 1 is equal to, and now we want to take the difference between these 2 points over here, okay? So they have the same x value, but the y value is different. So we have y2 plus y3 over 2 minus y1, okay? And all of that is going to be over, and now we're going to take the ratio of the smaller triangle of the difference here, this one, and that's going to be y2 plus y3 over 2 minus yg, okay? So now all we need to do is just solve for yg. Okay, so how do we proceed here? So what we can do first, let's multiply the denominator on both sides. So here we end up with 3 times, and here we have y2 plus y3 over 2 minus yg, and that is equals to, and let's actually find the common denominator again. So we have y2 plus y3 minus 2y1, and the whole thing over 2, okay? So let's first multiply 2 on both sides to get rid of so many fractions here. So this will become 6, okay? And I'm going to rewrite this here, yg, and that is equals to y2 plus y3 minus 2y1. Okay, so now let's distribute the 6. So if you if you distribute the 6 here, 6 divided by 2 is 3, okay? So that actually becomes 3 times y2 plus 3 times y3 minus 6 times yg equals to y2 plus y3 minus 2y1, okay? So let me actually add all of this. I'm going to add it on both sides of the equation. I'm actually not quite adding, but like, for example, I'm subtracting y2, I'm subtracting y3, and I'm adding 2y1, okay? So you end up with the following. If you subtract y2, you end up with 2y2. Subtract y3, you end up with 2 times y3. And then I'm adding 2y1, okay? And I'm going to subtract or add 6yg to go to the right side. So this becomes 6 times yg, okay? So let me erase this so it's not confusing. Now I can finally divide 6 on both sides and flip the equation again. So you end up with yg is equals to, and 2 divided by 6 is a third, right? So if we rearrange it, then we end up with y1 plus y2 plus y3 over 3. And there it is. We proved this one, okay? So we proved that the y-coordinate of the centroid is actually the average of the y-coordinates of the vertices of a triangle, okay? And we did the same thing for the x. So now we know that this theorem holds true. Okay, so we proved this theorem here. So again, in today's lesson, I know it was a little long, but we actually proved all these 3 theorems, okay? Now you're free to use them in algebraic problems, these proofs, okay? So please post a comment on this YouTube video if you have any questions. Also, click like if you enjoyed the video. Don't forget to subscribe to see more upcoming math videos. And again, have a fantastic day.